Applying a mathematical cipher to a file is a highly specific local action. Protecting an information asset is a continuous, system-wide discipline. You can deploy AES 256 encryption perfectly, but if you assign access to the wrong data owner or abandon a decrypted copy on a decommissioned drive, that mathematical strength offers zero protection. Today, we are constructing a complete data protection architecture from first principles. We will move step by step from assigning sensitivity labels to defining human roles, physical states, and technical baselines. Operational security cannot exist in a vacuum. It requires translating the strict governance frameworks of ISO IEC 27001 and NIST into concrete engineering realities. This diagram shows two side-by-side ladders representing data classification. The commercial ladder steps upward: public, sensitive, private, and confidential. The government ladder runs unclassified, confidential, secret, and top secret. Notice confidential marks the highest tier for a bank, but sits low for the military. Context defines control. However, there is a strict semantic distinction in these standards that routinely traps practitioners: the difference between classification and categorization. This logic diagram visualizes the difference. Classification applies directly to the data. It is the label placed on a specific file based on its sensitivity. Categorization applies to the environment. Under FIPS 1E9, you categorize an entire system by the impact its compromise would cause, rating it low, moderate, or high. If an architect treats a system impact rating as a file sensitivity label, they will miscalibrate the technical controls for the entire environment. Labels need people to enforce them. At the top of this organizational node map is the data owner, a senior business leader accountable for the data, setting classification and access rights. Below them is the custodian, the hands-on IT team that implements the technical controls mandated by the owner. Running parallel is the data steward, the role responsible for maintaining the data's quality, accuracy, and ongoing business context. Applying privacy standards like GDPR shifts the structure. A dual-node setup connects a controller to a processor. The controller dictates the why and how of processing personal data. The processor acts entirely on the controller's documented instructions, never improvising. And the data subject is the actual individual the data identifies. Mixing up these definitions is dangerous. If you treat a custodian as an owner, accountability vanishes, leaving technical teams making business risk decisions they are not authorized to make. 3 physical data states require independent defenses. First, data at rest on a disk is protected by full disk encryption. Second, data in transit across a network uses a VPN tunnel. Third is data in use. To process data, CPUs historically decrypted it. Now, confidential computing uses hardware enclaves to keep data encrypted during processing. These 3 states map onto a continuous sequence shown in this lifecycle loop. You create, store, use, share, archive, and finally destroy the data. Asset protection follows the asset. The specific technical controls must move with the data from cradle to grave. Treating encryption as a static blanket control fails audits. The defense must dynamically adapt to where the data physically resides at any given millisecond. The final phase requires precision. Standard deletion only removes file pointers. The actual binary data remains completely intact on the physical media. That leftover data is called remnants. It is highly recoverable, and it is a primary reason organizations fail compliance audits during hardware decommissioning. To eliminate remnants, NIST outlines 3 sanitization tiers. First is clearing, overriding media for internal reuse. Second is purging, using degaussing or crypto erase to shatter encryption keys, making it safe to leave the organization. The third tier is destruction, physically shredding the drive so it can never be used again. Deciding when to execute these methods requires balancing retention schedules. Legal hold forces you to preserve specific data for litigation, while data minimization policies force you to delete data you no longer have a legal right to keep. Relying on a standard trash bin without verifying destruction leaves your enterprise legally and technically exposed long after the hardware is unplugged. Translating these concepts starts with the security baseline. the minimum uniform floor of controls required for a system. First, you apply scoping, extracting controls that do not apply to your environment. Next is tailoring, adjusting, and strengthening the remaining controls to fit your specific operational risk profile. To enforce these tailored controls on the data itself, engineers deploy a specific technical toolkit. Data loss prevention, or DLP, monitors the perimeter and blocks exfiltration. Digital rights management, or DRM, enforces strict usage rights directly on the content. Tokenization strips out sensitive values and substitutes them with meaningless stand-ins, and a Cloud Access Security Broker, or CASB, acts as a centralized policy enforcer between your users and cloud services. To ensure this toolkit is deployed correctly, you must follow the governance hierarchy, illustrated in this descending waterfall chart. At the top is policy, the mandatory rule. Beneath that are standards and baselines, providing mandatory specifics. Guidelines offer recommendations, and procedures deliver step-by-step instructions. A generic framework is completely abstract until you scope it, tailor it, and drive it through this hierarchy. This schematic represents the unified result. We have integrated policies, human roles, physical states, and destruction mechanisms into a single cohesive engine. Asset management under ISO IEC 27001 is a continuous pipeline. It is not a fragmented list of technical features to be purchased and installed in isolation. Architectures collapse when technical controls are decoupled from governance. Encrypting a hard drive flawlessly means nothing if your procedures fail to purge that drive at the end of its life. Technical execution falters the moment these roles blur. A processor acting without explicit instructions from a controller breaks the legal framework entirely. By unifying rigorous data classification, precise role assignment, physical state awareness, and baseline tailoring, you transition out of simple compliance checklists. You build verifiable, durable engineering.